Hello and welcome to another video. In this video we're going to be going over shortest path visiting all nodes. So in this problem you have an undirected connected graph of n nodes labeled 0 to n minus 1, and you're given the array graph where graph I is a list of all nodes connected with I by an edge. Return the length of the shortest path that visits every node. You may start and stop at any node. You may revisit nodes multiple times, and you may reuse edges. So in this example here, node 0 is connected to 1, 2, 3, node 1 is connected to 0, node 2 is connected to 0, and node 3 is connected to 0. So there's a bunch of possible paths, but one possible path is 1, 0, 2, 0, 3. You can also, let's see what happens if we try at 0. So if we go 0, it's like 0, 1, 0, 2, 0, 3. Right, so it'd be 0, 1, 0, 2, 0, 3. Well, that's actually 6 nodes, so that would be worse. So any path starting at non-zero is fine. Now let's look at this one. So here there's a bunch of valid paths, right? So this would be one valid path. This would be length 5. There's a bunch, right? This one, this one. I guess that would be the same. Yeah, you pretty much have to start at an edge on the corner, and then there's a bunch of But pretty much what you have to do is you have to visit every single edge. And we need to figure out how we can even keep track of that state, right? Like how do we even make sure we prevent infinite loops and all kinds of things, right? Like what does even that look like? How do we represent the state of where we're at? And so let's actually solve a simpler problem first, and then we will go into the bigger problem. So let's say you have something like this. Let's actually do this. So let's just say we have something like this, right? And we want to get from one end to the other, right? So let's say we are here and we want to get to here, and we have some obstacles or something, whatever. Obviously here you wouldn't be able to do it, but it would be something like this. And so you're here, you're trying to get here. So how do we do this problem, right? And let's just say the length of every movement is 1. So this would be pretty straightforward. You can do two things. You can do a DFS or you can do a BFS. But if BFS is going to be pretty efficient here, right? So essentially what you would do is you would start at this node, and you would put this node into a queue, and then you would start visiting everywhere. And because every single node path is length 1, this is very important, you're guaranteed with a BFS, as soon as you get here from somewhere, that is the shortest possible path, right? You're guaranteed that. But if these nodes were more than one length, right? Like let's say this cost 8, and this cost 10, and this cost 20, then you can't just do a normal BFS, right? It wouldn't really work. Then you'd want to use a heap to find the cheapest edges, right? Kind of like we did in the problem yesterday. So that's kind of the main thing you want to look for in problems like this is, how expensive is it to traverse an edge? Are they all the same? If they are, BFS is better. And are they all different? And in that case, you need to use a heap, because just because you get somewhere first doesn't mean you're guaranteed to use that, right? Like let's say, actually we can draw this again, but in this example, let's say we are even here, but the cost of this is 100, and we can literally be here really quickly, but the cost of some long path is 1, 1, 1, 1, 1, 1, 1. We would get here first with a BFS, but that doesn't guarantee our result. But if everything has the same cost, then the one we get to first with a BFS would give us the right answer. So notice here, you want to calculate the length of the shortest path that visits every node, and the cost of moving from node to node is always 1, right? These aren't variable. So that is going to mean we're going to want to use BFS. But it's not that simple, obviously, right? So for BFS, obviously you can start at every single node. You can do that, right? So you can just say okay, well, let's just start at every node, and let's try to get to all the nodes, right? Let's just put every single starting point in a queue, like a normal BFS. You could do that. You can put in multiple starting points, and you can just say, okay, well, let's just start at every single node, and then once we get to all the nodes, then we can return that. But how do we even do that, right? How do we even remember what states we visited? What don't we want to do multiple times? What is even a state? Things like that. And so for these problems, what I noticed is for these hard problems that have low constraints is something that's really useful, and I think I've seen a bunch of these by now, is when you have like a bunch of nodes, but that's not too many, or like keys, there was a problem with keys or things like that, right? You have like 10 to 20 roughly things you need to visit. What you're going to want to do is you're going to want to use a bit mask because it's going to be the best way of representing state. So if we have a bit mask, and let's say we have 12 nodes, it's going to be the best thing to represent which things are visited. So for example, let's say we don't have 12 nodes. Let's say we have like nodes 0 through 5, right? So we can literally just have 6 zeros that represent every single node, right? So this would be, and then you can do it in whatever order you want, but in my case, I'll have the rightmost node be node 0 and so on, right? So, for example, what we can have here is we can have this is node 0, this is node 1, this is node 2, this is node 3, this is node 4, this is node 5, and this is just one big number. And that's pretty straightforward, and we can use a bit mask to represent that. And then, if we want to say we visited node 2, all we have to do is turn on the node 2 bit to 1. And that one's pretty straightforward. So to turn on a bit is really straightforward because all we need to do is just, so let's say we have a 1 here, right? We have a 1, and then all we have to do is shift that 1 left n times where n is the bit we want to use. So if we want to have bit 0, then we would shift it left. You know, we basically shift 1 left n times. So if it was 0, we'd shift 1 0 times. Then we would OR this. So you want to have an OR, and then what that would give you is 0, 0, 0, 0, 0, 1, right? So if you want to turn on a bit, meaning if you want to visit it, it's pretty straightforward. You just shift 1 n times for whatever node you want to visit, and that's how you could visit it. So that helps us solve that problem, right? We can use a bit mask to represent the nodes we visited. But just because we know the nodes we visited, do we need any more information? And yes, we do, right? Like for example, let's say we visited in this example up here. Let's say we visited this node, this node, this node, and let's say this node. Well, does it make a difference if we are over here or if we are over here, let's say, right? We visited the same amount of nodes, these 4 nodes, but it does make a difference depending on where we are, right? If we're over here, then we can get here with 1 move, and if we're over here, then we can get here with 2 moves. And we are allowed to like revisit nodes and edges, so you can't just say just because you visited something, you can't know where you are. So you have to know 2 things. You have to know this bit mask of visited nodes, and you also have to know your location. But once you know that, those are all equivalent, right? So let's say if I visited these 4, and I'm over here, anytime I get to this state, they're all going to be the same, right? It doesn't matter where I got to this 4 from. As long as I know what nodes I visited and what node I'm at, that represents the totality of the state, right? That's all we need to know. So for one thing we can do is we can store this, so we can actually store, let's say, this bit mask and the location in a set. So we would have like location and then bit mask. And then this would be like a state that we can store in a set, right? To make sure that when we get here again, we don't do any kind of calculation. This can be like our cache. So we can say cache, this represents our total state. Our location, like where we are, and the bit mask of all the nodes we visited so far. That's all we need to know. Okay, well now that we know like we kind of want to use a BFS and we want to start at every single node and this is how we store the state. Well, what do we like how do we end, right? Like how do we get to a solution, and also what do we return? Well, let's think about it. So let's say we have 6 nodes, right? So if we have 6 nodes, what does our final state need to look like for us to return? Well, all these nodes need to be visited, right? And how does that look? So let's actually have this a different color. So it looks like this. So it's 1, 1, 1, 1, 1, 1, meaning all of these are visited, right? And how do we initialize something to that? Well, that's also pretty easy. You can literally just shift left 1 n plus 1 times, right? Actually, in this case, if n is 6, if n is like the total number, you would shift left 1 n times. So let's see what that would look like. So it'd be 1, 0, 0, 0, 0, 0, 0, I think. Yeah, because yeah, it's 1, 2, 3, 4, 5. Yeah, okay. So it would look like this. And now we can simply subtract 1. And if we subtract 1 from this, then we get 1, 1, 1, 1, 1, 1, right? Because essentially you subtract 1 here and all of these would turn into 1s. So that's how we can get like the final state we need. We can take the n that we want, shift left 1, that many times, and then we can subtract 1. And that would give us the final state. So we can simply compare the bit mask of that we have to the final state, and we're guaranteed in a BFS, remember, to always get to the like final answer in the fastest amount of time, because every single path length is 1, and that's critical to our problem, right? If every single path length was different, you wouldn't be able to do a BFS. You'd have to use like a heap. Okay, so now we know kind of like what we need to be doing. We can cache our location and our bit mask. So how do we actually know where, like once we get to the bit mask that we want, once we get to this, how do we know what to return, right? Because we're asked to return like the number of steps taken. How do we know that, right? Well, it's going to be pretty straightforward. We are going to store 3 things, actually, instead of a location bit mask. We are going to cache the location and bit mask, but we're going to store in each element, we're going to store location, bit mask, and we're going to keep track of the steps we took, right? And that part's going to be pretty straightforward, because every time we go somewhere, we can just add 1 to the steps. So we'll start with 0, and we'll just add 1 to the steps. And essentially what's going to happen here is our initial state is going to be, we're going to put in all of these as a bit mask, right? So let's give us an example of this 0, 1, 2, 3, for example. Let's see what that would look like. So we have 0, 1, 2, 3. Let's kind of walk through this. So let's actually make this, right? So we're going to put this into the deck. So let's do that. And I'm just going to do like a few steps and then kind of show you what it's going to look like. We don't need to do the whole thing. But essentially, we're going to put in all of these as possible starting points, because they could all be valid starting points. We don't know. So we need to put in every node as a starting point. So for the location, what are we going to put in? Well, that part is pretty straightforward, right? We're going to want to put in 3 things. Like I said, we're going to want to put in the location. So like for 0, for example, we'll put in 0. Then we need the bit mask. What's the bit mask for 0? So if we started 0, we visited 0. So the bit mask for 0 is going to be 0, 0, 0, 1. Obviously, this is going to be a number, but I'm just representing it as a bit mask. And the steps is 0. We haven't moved anywhere yet. Then for 1, same thing. We're going to have 1. Then the bit mask for 1, which is 0, 0, 1, 0. Then 0. For 2, so we are at node 2. Bit mask for 2 is going to be this. 0. And finally for 3. 3, 1, 0, 0, 0, 0. And now essentially what's going to happen here is, like I said, I'll do a few of these. So we are going to put these into the set, right? So we'll have these all in the visited set. So we can literally say like, okay, our visited set is going to contain these. It's not going to contain the steps. We don't care about the steps. All we care about is, like I said, the location, the bit mask. That's all we need to know. And we're not going to like retrieve anything from the set, but anytime we get one of these again, we're just going to skip it essentially. So what's going to happen here is, let's actually draw our set maybe over here. So our set is going to contain 0. And the reason we also need to store these as tuples, because we want to store like values that are immutable, right? So instead of these being arrays, we'll just store 3 or like 2 integer tuples or whatever, right? So essentially our set is going to contain 0. This is going to be 1, and it's going to be 1, 0, 0, 1, 0, 2, 0, 1, 0, 0. This will be our visited set, pretty much. 1, 0, 0. Okay. So now, essentially, let's just go through kind of like the process of what happens for a few of these. So let's say we pop out this number right here. We pop out 0, 0, 0, 0, 1, and 0. We pop it out. It's no longer in our deck. First, we have to check, is this equivalent to our final state? Well, no, it's not. It needs to look like, so our final state in this case with 4 numbers needs to look like 1, 1, 1, 1. It's not that, right? Then we need to check, where can we go? So when we're at 0, where can we go? Well, we can go to 1, 2, or 3. So we actually have to try to go to all of those. First, we have to check, are those states in the visited set? And if they're not, we have to add all of them to the deck. So let's actually get rid of this just so we have more space. So if we try to go to 1, what would our state look like, right? So we would be at 1, then we would turn on 1, and we would have 0 turned on, and we took 1 step. And we can check, is 1 and 0, 0, 1, 1 in our visited set? No, it's not, right? So it is not. So we have to add that to our visited set. And then we can also add it to the visited set because it's in our it's in our deck, and like once you have this in the deck, you don't need to actually pop it out. You can just add it to the visited set right away. So we're gonna add 1, 0, 0, 1, 1, and that's because in the deck you're guaranteed to get to a number faster if it's further up in the deck, right? It's a deck, so this isn't like a heap. So for a heap, you would wait till you pop it because you might have something in the heap earlier that comes out later, but for a deck, it's just first in, first out, right? So if it's in the deck, you're guaranteed to get it first, so you don't need the rest of the stuff. So what would happen here is we would put that into our deck, or put that into our visited set, and then remember we need to keep this. So we're going to actually take this, and now we can put it into our deck. Now we also need to try to go to 2. So what would 2 look like? Well, it would be at 2, and then it would be 0, 1, 0, 1. It would be 1 step total so far. And we can check, is 2 and 1, 0, 1 in our deck? No, it's not. So we would add that in as well. So it would be 2, 0, 1, 0, 1 would be in our visited set. And then we would put this in our deck as well. So we'd put that in our deck over here. And now we also need to try to go to 3. But you can see how this gets really big really fast. So I'm going to stop after the 0. So we need to try to go to 3. So for 3, it would be 3, and then it would be 1, 0, 0, 1, and then it would be length 1. Right? So you keep doing this, and essentially, eventually, you get to a point where you get to your final result. So this was like our new deck now, where we pop this out, and we did this, right? And you keep doing this, and you keep doing this, and you keep updating your state, and it's pretty straightforward, right? Every time you visit something, you just turn on that bit, and then you check, is the combination of the place you're going and the bit mask in our set? If it's not, we don't even need to put it in our deck, we can skip it. And if it isn't, then we need to do that, right? So you pretty much just keep going through your deck, There's a guaranteed answer, and it's also guaranteed that everything's connected, so you're never going to have like an island or something. You keep doing that, and then the first place that matches the bit mask of all ones is guaranteed to be your result, because that's how BFS works, assuming all the path lengths are 1, which they are. Okay, so now we have enough to code it up, and I'll go into the code and kind of explain it a little bit more. So it's full screen. So let's first use an n here, because we're going to reuse that. So let's just make sure it's tabbed correctly. Let's say n equals length of the graph. Then let's make a final mask, which is like what the bit mask needs to be to actually get a result. So it's going to be 1 shifted left n times, like I said, minus 1. Then we need to make our queue, which is going to be a deck. So it's going to be deck, and it's going to be a bunch of arrays, essentially. So it's going to be I, 1 shifted left I times, because this is going to be all the default starting nodes, which could be any node in it, right? So 0, 1, 2, 3, 4, 5, and so on. So we're essentially shifting 1 different amount of times to indicate that that default starting node has been turned on. So we need to do that. So for I in range n. Then we need to make a visited set to make sure we don't revisit the same nodes that have the same mask on. So we can make a visited set. We'll just say visited equals set, and it's going to take a tuple of I and 1 shifted left I times for I in range n. Range n, just like this top part, except we don't need the steps in the visited set. We don't really care. We just need those 2 things. So then while our queue is active, we are guaranteed to get a result here, so we don't really need to return something at the end. So essentially we need to get 3 things out of here, right? It's going to be the node, the mask, and the steps. It's going to be queue, pop left. And we need to check, is the mask the final mask? If it is, we can just return, right? So if mask equals final mask, we can just return steps. And then finally, we need to actually check for neighbors in here. And we can also check if we've seen the state before, right? So we can check the state here if we wanted to, right? But essentially, I don't think we're ever going to get a case here where we've seen the state before, because we're going to handle that. I'll show you like running into the queue. So we're never going to have a case here where we've seen the state before. We're going to handle that before putting things into the queue. So what that's going to look like is we're going to say for neighbor in graph node. We need to make the new mask, right? So it's going to be new mask. It's going to be mask ORed with one shifted left, whatever that neighbor is, whatever neighbor we're going to. Then we need to check if that tuple that we're storing in the set, right? So it's going to be wherever the neighbor is. So neighbor location and the new mask is not in our visited set. Then we need to add it in, otherwise we can skip it. So we don't need to check if the node we popped has been visited, because it will never be visited, because we're essentially taking care of that down here, where we're just making sure we're not putting these items into the queue that are in the queue already. So we can say visited.add neighbor new mask. And we can append it to the queue. So we append neighbor new mask, and we add one more step to the previous steps. And so you can return if you wanted to, like return -1 or something, but it should never basically get to that point. So let's see how that goes. And we can actually exit this maximize, so it looks like it worked. And it looks like it's reasonably efficient, as you can see. So let's go through the time and space for this one. And yeah, I don't think it's, well, actually, I mean, it's definitely a hard problem, but is it like a super intense hard problem? Not really, especially when you do this BFS. I think it's a lot more intuitive to do a BFS than like a DFS in this one. If you just simplify it down to, like I said, a problem where you're just trying to get from one point to the other. The only difference is you have to check for this final mask, which is definitely kind of tricky to figure out. Okay, so for the time, what are we doing, right? So this is going to be, final mask is going to be O of 1. So for this deck, this will be O of n. For the visited set, just initializing it will be O of n. But then, like, how many total things can we have in the deck, right? So we're never getting duplicates in our deck. So if you think about it, how many total things can we get here, right? So our node and our mask, like this state, will never be repeated, essentially. So because the state will never be repeated, the number of states in our queue is whatever the number of possibilities for the node and the mask are. So for the node, that's n. And for the mask, that's 2 to the n, right? Like when we make this number, it's a bunch of zeros that are equal to n. And so these can be on or off. So each one of these is like a new bit. So if you have n bits, that's 2 to the n of like the size of your number. So the total different elements that can be in the queue is n times 2 to the n, roughly. Okay. And for the space, it's the same thing, right? Like the number of elements we can have, that's like their big thing that is our issue. So it's going to be n times 2 to the n. Because it's the same kind of thing, like these two will always be unique. So we can have n times 2 to the n different things in the queue for the time and the space. Which is pretty efficient for this function because as you notice here, n can only be 12, right? So it's not that big, it's like 2 to the 12. That's another kind of like important thing to notice is when you look at constraints that are really small, it indicates your solution's probably going to be like 2 to the n or 3 to the n or something super inefficient, right? They're not going to give you like, for a hard problem, they're not going to give you something that n equals 12 and it's just going to be like an n squared solution, right? It's always going to be kind of like pretty unoptimal. So that's like another hint you can use to figure out that you're probably, you can have a quite inefficient solution and it will still pass. But yeah, I think that's going to be it for this problem. Hopefully you liked it. Definitely a good problem. I would strongly recommend doing it, I think. And if you did like it, then please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.